Okay, everyone. We start from page 29 on the slides. So we look at exercise 9.6 and 9.7. And for 9.6, it showed that the condition D1 off and D2 on, and it's not valid. Okay. So in for this, wait a minute. For this kind of problem, we assume it's an ideal dial. So we assume it's ideal dial. And if it's ideal, if it's when it's under forward bias, it's under forward bias, and the dial is on, it means it is short circuit. We need to check if I is larger than 0. So suppose this is a dial and this is I. How about I use this? Suppose this is a dial, then this is positive. On the bottom of the triangle is positive, and so this is V. We say VD, and then we assume a direction of current. This is ID. So check ID larger than 0. Okay, this is the first case. Second case, if it's under reversed bias, and it is off, and then we assume this dial is an open circuit, and we need to check if VD is smaller than 0 because it's open circuit. And so we look at exercise 9.6. So show that the condition D1 off and D2 off is not valid for the circuit for this circuit. So D1 off, D2 off. So we for this 9.6, we redraw this diagram. So this is 10 volts. This is 4K ohm. So if they are off, that means they are open circuit. Okay, and this is also open circuit. Okay, then we say this is 3 volts and this is 6K ohm. Okay, and we need to define VD1. So this is a positive, negative VD1 because this is we define the bottom of the dial is positive, so this is VD2. Positive, negative VD2. Okay, we just need to check if VD is smaller than 0 because they are off. Okay, so what we can do here, we can have a ground. So this is we connect to a ground. So suppose this is 0 volt, and because these two loops they are not a closed loop. So which means there's no current. For example, there's no current flowing into this 4K ohm resistor. So I know I use a different color. I know here at this point it should be 10 volts, right? Because this is 0 volt, this is 10 volts here, and then because there's no current, it doesn't come, this resistor, this 4K ohm resistor doesn't consume any voltage, so this is 10 volts. And for 0 volts, here is also 0 volts because there's no current flowing through this 6K ohm resistor. It means no voltage is consumed, so 0 volts. And for 0 it go across these 3 volts voltage source. So I here is 3 volt. So we know VD1. So I go back to this color. So VD1 equals uh, 10 minus 10 minus 0 is 10 volts. So the voltage difference between D1 is 10 volt. It's a forward bias, right? Okay, and VB2 is 3 minus 0, positive minus negative equals 3 volts. They are all forward bias. However, we assume D1 off, D2 off. So they should be reverse bias. So they are invalid. So we show that this D1 off and D2 off is not valid. Okay, so this is 9.6. And then we look at example 9.7. Show that condition D1 on and D2 on is not valid for the circuit of this figure. Okay, so same thing. If both of them are on, then they would replace short circuit um, with the diodes. So we redraw this circuit diagram. 4K ohm. So we replace a short circuit. But we need to give a direction of current is ID1, right? Because the direction of the dial is always here. We do not consider the breakdown voltage. If we do not consider breakdown voltage, then the direction of current is only one direction. Okay, so we make it short circuit and we assume a direction of current. And so this is short circuit. Okay, this is 10 volts. This is 3 volts. And short circuit, the direction of current is ID2. If they are close, then we need to check if direction of current are positive values, right? So how can we check? So same thing, we define a ground, so it's 0 volts, and how? Um, so we have if this 0 volts and uh, okay, how can we do? Okay, so by observations. So this point is 0 volt, right? And then we go across, when we go across a 3 volts voltage source, which means at this point is 3 volts. And then because they are short circuit, which means at this point is 3 volts. Okay. And because we assume that this wire doesn't consume any energy, so they are same voltage. And then we look at another branch, 0 volts, go across to 10 volts. So this is 10 volts. Okay, so for this 4K ohm resistor, we know the voltage at both sides. So we can calculate the voltage difference, which means we can apply Ohm's law. Okay, so Ohm's law. So we have, so IT1, the current goes through this 4K ohm resistor equals 10 minus 3 because we want to check if ID1, the polarity of ID1, and we want to check the value of ID1. So 10 minus 3 divided by 4K is 7, 7 over 4 milliampere. Okay, so it's a positive value. Okay, so it might have a chance. And let's look at here because we want to know ID2. But for this, we need to suppose this is I3. Suppose this is I. So we can calculate I, right? Because we have I equals 3 minus 0 divided by 6K, which is 0.5 milliampere. So how can we solve ID2? Yes, by KCL, right? So we just apply KCL and its node. So KCL tells us the summation of the current flowing into a node equals the summation of the current flowing out from that node. So the current flowing into this node is ID1 plus ID2 and equals I. So since ID1 is 7 over 4 milliamp, and then we have plus ID2. Okay, I just said 7 over 4 equals 0.5. So ID2 equals 0.5 minus 7 over 4, which is minus 1.25 milliamp. So this is invalid. Okay, so because if we assume the diode is on, we assume both of the diode is on, then um, then we need to check the current flow into this diode is positive value. But it turns out one of them is a negative value, so the assumption is not valid. Okay, so you need to so if we want to know uh, the if if you want to know which dial is on, so you can get rid of D1 off, D2 off. You can get rid of D1 on, D2 on, and you may try D1 on, D2 off, or you can try D1 off, D2 on. So you need to check you have 4 options. So you need to check all of them. And until you find out there's one condition that's that's satisfy your assumption. And that's the answer. There will only be one answer. So okay. So although we do not actually find out the correct answer, but I already show you how to get rid of the false assumptions. All right. And then we look at the next problem. Find the diode states for a circuit shown in figures 9.17, 9.17. Assume ideal diodes. So you need to know the assumption, you need to assume ideal diodes. So for ideal diodes, just like what we solved in the previous slides, for ideal diodes, so so okay, let's look at A. So for A is simple because it just it just has one diode, right? And then so if it is so here V1 and we have this I VD VD ID, okay, and it is VD and then this is ID ID of VD1 ID1. Because for A, I can immediately recognize that this dial is on, but in order to follow our previous assumption, I mark VD1 and I assign a direction of ID1. And then, so here we know this is 1K times ID1, right? The voltage. So if it is on, if it is on, so for ideal dial, uh, when it is on, it's a short circuit. When it is off, it's an open circuit. So if this is on, so we assume on, assume D1 on, and then so this is short circuit. So we know 2V. So if it is short, I need to anyway. So assume DI1, we need to redraw this. I use the very primitive solution. So we assume this is short, and this is positive negative, 1K ohm, and this is ID, and then this is 1K. The voltage here, this is 1K times ID1, ID1. So by using KVL within this loop, we have minus 2V, we have minus 2 plus 1K times ID1 equals 0, and then ID1 equals 2 milliamp, which is positive. So the assumption is valid. So this is the right procedure to solve, although you don't need to do that because it has just one dial. This is way too simple. If it's an ideal dial, then we know it's under under a forward bias. Okay, because and the current will always flow in this direction because um, assume this is zero, the voltage, the electric potential at the bottom of the triangle will be always larger than the electric potential here. So for this, I know it's under forward bias. So D1 is on. So you don't even need to make a thorough analysis. Then we know D1 is on. D1 is on. And for B, it's obvious that because this is positive here, and you connect the negative to this diode, so we can know immediately that D2 is off. And if you are uncertain, you can assume D2 is off, and then same thing, you write the you write this circuit diagram. This is 2K ohm, and then this is off, and then this positive negative V1G, and then so this is assume this is 0 volts. We always assume we'll connect this negative terminal of the voltage source to the ground. So, and because there's no current flowing into this diode, we have this is 0 volts here, and here is 3 volts. So VD1 equals 0 minus 3 equals minus 3 volts. So which is under reverse bias. BIS. So the assumption is valid. Okay, but if you are certain, if you have right concept, you should immediately recognize that this D2 dial, it is off. Okay, and so, but for problem C, we can only make assumptions. We have four choices, but you need to start the most possible option, right? So we so here we have a voltage source. This is positive, so it's 10 volt. 10 volt is quite large, right? So since the positive terminal connects to the positive side of this D4 dial, then it's very likely that the D4 is on. Okay, so we assume D4 on, and let's try D3 on. Well, although I don't know which one is maybe. Okay, so we say this is 5 milliamp, 2K ohm. Then assume this is on, right? We assume this is on. If it's on, we need to check the direction of the current. If it is on, we need to check the direction of the current. It's called ID3. ID3 is called ID4. So we define the direction of current. And then this is positive negative 10 volts. This is 1K ohm. Okay. Um, how can we solve this? So we need to if we define, so here, let's see how can we, well, it seems we may need some work. Okay. So we make it ground. This is 0 volts. And here we don't know. So we say it's V1. And here we know it's 10 volts. You should learn this in electrical engineering. It's called nodal voltage analysis. And we use this example as a review. Yeah, it's not very, if you do not learn well previously in the previous class, you may have some difficulties to analyze this. Okay, so let's see. Uh, wait a minute. So we look at node 1. So suppose this is node 1. So KCL at node 1. KCL at node 1. So we have, so we assume that the current flowing into node 1, the summation of current flowing into node 1 is 0. So we have 5 MA, so 0 0.005 uh, plus uh, 10 minus 10 minus V1 plus 10 minus V1 is a good way to show okay, divided by 2K, and then plus 0 minus V1, and then divided by 1K equals 0. And you should be able to find out V1. And once you find out V1, and then, okay, that's no matter how, let's do it. So V1 is, okay, so V1 is, so multiplied by K. So we have 5 plus, this is 5 plus 5 equals 1/2 plus 103 V1. 3 V1. So V1 equals 10 times 2 divided by 3, 6.67 volts. So V1 here, 6.67 volts. So how about the direction of ID3? So how about ID3? So ID3, so we can calculate, since we know the voltage across difference between these 2K ohm, and then so we know ID3 can be calculated as 6.67 divided minus 10 divided by 2K, which is 6.67 minus 10 divided by 2 is minus 665 milliamp. Therefore, it is invalid. Okay, so the assumption is incorrect. And so we need to assume another condition. So we assume, but D4 should be on. D4 should be no problem. So we assume D4 on, D3 off. Okay, so we redraw this circuit diagram. So we have this 2K ohm. So this is off. Then you have positive, negative, VD3, and D4 is on. So we draw the direction of current, this ID4, and then this is 1K ohm, and there's a voltage source, 10 volts. Okay, how about this case? Um, in this case, I use different color. In this case, we observe there's a loop, right? Since there's a loop and it has a current source, 5 milliamp, it means, and because this break, there's no current flow through this middle branch, so which means we know immediately that this ID4 equals 5 milliampere, so it's valid. And then, but we need to check VD3. So how to calculate VD3? So here, because we already know the direction of the current, and then we know the current is 5 milliampere. So we know this positive, this is negative, because a resistor always consumes energy. So we have 1K times 5 milliampere, and you got 5 volts. Okay, and then but we don't know the voltage. Let's assume this is V1, and so by applying KVL, so KVL says within any loop in a circuit, the summation of the voltage of each element should be 0. So we're starting from the bottom left corner, and then so we have minus V1 plus 5 minus 10 equals 0, and go back to the same node. So V1 is minus 5 volts. So which means, so V1, V1 is minus 10 volts. So here, right, V1 minus plus 5. Okay, V1 is minus 5 volts. So V1 is minus 5 volts. So minus 5 volts. So this is minus 5 volts. So we assume if this is 0 volts, so 0 volts go across this voltage source. Here is 10 volts. So VD3 should be minus 5 and minus 10 equals minus 15 volts. And it's reverse bias. So this is valid. Okay. So both of them are valid, which means the assumption is correct. So the problem for C is, the answer for C is D4 on, D3 off. Let's see if it's correct. So this is 9.8, exercise 9.8, D3 off, D3 off, D4 on. Okay, that's how it is done. So you need to be very clear. So this is 10 volts. Here is minus 5 volts. Oh, wait. This is 10. Oh, this is 5 volts. You see, I could easily be wrong. If we assume this is 10, then we go across this 5 volts, resistance. So this is 5, should be 10. So VT3 is 5 minus 10. 5 minus 10 was minus 5 volts. But it's still valid because it's reverse bias. So it is valid. Okay, this is valid. Uh, a little bit messy, but hopefully you know how to solve this kind of problem is you make assumptions and you need to redraw the circuit and then calculate and then try to validate your assumption. Hopefully we have some problems in your homework. Uh, it looks a little bit tedious, right? And okay, um, if you still have problems, you can ask me when we have an online lecture. We look at the next page with next slides. We covered this previously. So basically, this is Zener dial. And so this problem, it asks you to sketch I versus V for this circuit. So to remind you again, for this is the dial. And then we usually assume the bottom of the triangle is positive, negative, and this is V, and this is I, and we, if it's not ideal, we'll give you this is V, this is I, so there's a VI curve, and here it says what? So there's a threshold voltage or knee voltage of 0.6 volt for all the dial, which means this is 0.6 volt. Okay, including the Zener dial. Okay, when current flows in the forward direction. So we have Zener dial. So for Zener dial, so still this is positive, this is negative. Suppose this is V and this is I. So for Zener dial, its characteristic is VI curve should be, because it says the forward direction includes the Zener dial. So for Zener dial, under the forward bias, it should look the same as the normal dial. But here it has Zener voltage. Here, for this case, this is 6. Okay, but this case, this is 5.6. So we just say this is VZ. Okay, so we have these two kinds of VI curve. So for A, we talk about this in the class. For A, you see, for this is when V is larger than 0, this dial is under forward bias. So we can have a VI curve. This is V. This is I. And then, so if V is larger than 0, so we look at this dial. So here, but at this moment, this is off, right? Because it's under reverse bias. So it's just like this. Positive, this is V, this is I, and this is an open circuit. Okay, so we just need to focus on this diode only. And then since it's a forward bias, then the curve is just like this curve. Wow. just like here. Um, this curve and this 0.6 volt. Okay, and when V is smaller than zero, which means we're focused on here. When V is smaller than zero, so this is V larger than zero. For V smaller than zero, uh, how about I draw it here? When V smaller than zero, and then at this moment, this is the first dial is an open loop. So this is positive, negative V, but the second dial is on. So we focus on this dial. And so for this dial, and then so it becomes so so when V is smaller than zero, for this dial, when V is a negative value, it means it's under forward bias. Okay, but the current is defined in this direction, which means, but actually, in fact, the current will flowing in this direction, which means the current is a negative value, and then, my bad. And then, so it turns out that it is this. Oh, this is, and this minus minus 0.6 volt. Okay, so for positive volt, positive V, and this dial is on, this dial is off, and for this dial, you just follow the curve of the forward bias, and for V is smaller than zero, then this dial is off, and we look at this dial. So for this dial is under forward bias, but it just look but this V is negative and I is also a negative value. So the curve is just like this. Okay, so this is the solution for problem A. And for problem B. For problem B, we look at this is a dial. So the characteristic diagram of dial is just this. But it has a Zener dial in opposite direction of this dial of the first dial, and the Zener voltage is 6 volt, which means the 6 volt. It means V not just need to overcome this threshold voltage, but it also need to overcome this 6 volt Zener dial in order to be on. So for B, the VI curve for V will be like this, will be like this. Sorry, so this is V larger than, will be like this and like this. If it's under reverse bias, it's always off, but you need to overcome 0.6, not just 0.6 knee voltage. You need to plus the Zener voltage. The Zener voltage of this Zener dial equals 6.6 volts. For this dial to be on. So the VI, so the VI curve becomes this one. Okay, you need to, so if you put a Zener dial in the opposite direction of the dial, and so the VI curve, you not only need to overcome this 0.6 volt threshold voltage, but you also need to consider the Zener voltage of this Zener dial. So this is the solution for problem B. And let's look at problem C. Okay, for problem C, and so because in this problem, it also assumes 0.6 volt for all diodes, including the Zener diode. So for problem C, so here, if V is larger than 0, and then you need to overcome the threshold voltage of the first diode, which is 0.6 volt. But it also need to overcome the Zener voltage of this diode. So here at this moment, the Zener diode is function like the normal diode because it's under forward bias. So for C, we are able to draw the VI curve like this. And then, so VI curve, this is I, and then we have this. Okay, this is forward bias, and then this is 0.6 plus 5.6, which is 6 volts. And if when V is smaller than 0, so at this moment, this Zener diode, it works as a normal diode, but it also need to overcome the 5.6 volt Zener voltage. So it will become like this. Here, it should be minus 0.6 minus 5.6, which is minus 6 volts. So this is the VI curve for C. Hopefully you can understand. Okay, um, let's look at one more problem. Okay, it's called piecewise linear diode models. And sometimes, because previously we talked about how to solve this current and voltage of dial graphically, and sometimes we use these linear equations to approximate the curve. And here, and so suppose this is a VI curve of a Zener dial. So you see this is a forward bias, and here it is this is forward bias. This is forward bias here. So this segment A, it is forward bias, and segment C, it is reverse bias. And in the middle, because I equals 0, right? I equals 0, then it is open circuit. So we use this to approximate a Zener dial, although it use a symbol of a normal dial here because it has this reverse bias region. And how can we approximate? We look at how can we approximate this line? So this is VD ID. So for this line, the slope is 1 over R. And so actually, the line, its function, this line function is this. We have this, or more correctly, we have VD equals RA times ID plus VA. So for this, how do we find RA and VA? Because we need to find out the equation of this line. So when VD is 0, how about when ID is 0? When ID is 0, VD equals VA equals what? the intersection here is 0.6 volt, 0.6 volt. And when VA is 0, okay, when VD is 0, VD is 0, and then so ID equals minus ID equals minus VA divided by RA. But here we actually need to check this because it gives you this point, right? So we have so here we know VD equals 0.6 volt. So we have VD equals RAID plus 0.6. And RA here, actually we can calculate RA. RA is this is, so the slope. The slope is 100 amp divided by 1.6 minus 0.6. It should be 1 over R. So R should be this is 1 divided by 100 N. So it should be 100K. So we find out the equation here. The equation here should be, so I'm talking about this equation. The equation should be, so VD equals 100K. No, it's not 100K. It should be 10. It should be 10. This is 1 over 100 N. It should be 10. 10 ohm. 10 ohm. So this is 10 times ID plus 0.6. So this equation should be VD equals 10 ID plus 0.6. So we can have an approximate line of this IV curve under forward bias. So it says if it's under forward bias, then this diode can be replaced by a resistor plus in series with a voltage source. This is so this is the equivalent circuit when it is under forward bias. Okay, and then the same thing, we can approximate this line. Okay, the way is this is 1 over R. Same thing, this is 1 over R. So by calculating the slope, you can find out IR, and the intersection here is VA. So VA is minus 6, so we calculate R. So 1 over R should be the slope. It rises by what? 100 M, 100 M, and then this is minus 6 minus 7.2. So it should be what? It should be 100 M divided by 1.2. Okay, so R equals 1.2 divided by 0.1, which is 12 ohm. Okay, so we can write, so here, so the equation should be VD equals 12, and the intersection 12I2 minus 12 12ID minus what? Minus 6. And yes, we find out the curve for this reverse bias. And we double check when ID is minus 100 MA. So when ID, we double check. So 100 MA is 0.1. So we have, so if this is 12 is minus, so this is 12 times minus 0.1 minus 6 equals minus 7.2. So correct. So this is this point, right? So we find out the equation for this reverse bias. Okay, and here is just, we just use I equals 0, we just align to approximate. So we find out this segment, the equation for this segment, the equation for this segment, and the equation for this segment. So we use 3 segments of straight line to approximate the IV curve of a dial. And hopefully you know how to solve it. And let's look at, okay. And then we are going to stop here. But all right, how about before we leave, we introduce an example. Okay, so here we introduce how to use line segments to approximate an IV curve of a dial. And next problem, we want to solve it. So use the circuit model found in previous example to solve the circuit in this circuit diagram. How can we start? So first, we need to identify uh, which region does this diode uh, is working, does this diode work? Here, apparently, this is a simple example. Apparently, it's under forward bias, right? Why? Because if we always assume the negative uh, voltage source, the negative terminal of voltage source connects to the ground. This is 0 volt. And since this, and the current should flow from this direction, which means the current will go through this dial. So this dial should be under forward bias. So since it's under forward bias, then we find out this line. Previously, in the previous example, we already find out this line equation. This line equation is this line is actually here. So this line equation is VD equals 10 ID plus 0.6. Because it's already show you here. So if it's like a line like this, it means this line equation is 10 plus 0.6. And if it shows like this, then it means the line equation here, VD equals the resistor. This is the equivalent resistor in series with a voltage source. ID, and because it's minus, it's in the opposite direction of the polarities of this diode, so which means it's minus 6. So it's here, assume it's given to you. So you have the line equation, and then you need to write another equation here by the configuration of the dial. So we look at the configuration of the dial. Suppose we have ID and we know the direction of the current. So here we have positive, negative, 20 times ID. And we have positive For the diode, we have positive, negative ID. So by using KVL, so starting from the bottom left corner, we have -3 plus 20 ID plus VD. This is VD. This is VD plus VD equals 0. So we have VD equals -20 ID plus 3. So can we draw this line? This is a line equation, right? Can we draw this line on the IV curve here? Yes, we can. For ID equals 0, VD equals 3. So ID equals VD equals, it might be here. It might be this point. Okay, so it might be this point. And when VD is 0 and ID equals 3/20. So it's a positive number. It approximates 3/20, 0.15 ampere. This is 0.1, right? 0.1 ampere. So it might be here. 0.15. It might be this point. So we can connect these 2 points. We can find out an intersection here. This is the ID, VD. This is the answer, right? The intersection of the curve and a line, it is the solution. So, which means we have the equation of this forward bias. We have this line, and then we have this load line. Previously, we called this load line. Okay, so we solve these two. So we have 10 IB plus 0.6 equals -20 ID plus 3. So we have this 30 ID equals 3 minus 0.6 is 2.4. So ID should be 4 divided by 30, 0.08 ampere. Okay, so we got our solution. ID, the current ID here for this solution is 0.08. And if you want to solve VD, so VD is -20 times 0.08 plus 3 is 20 minus 20 times 0.08 plus 3 equals 1.4 volts, and it's under forward bias. Which means this is this point. At this point is 0.08. Okay. And then it's 1.4 volts. Apparently it's something like here. So which means, but anyhow, this is the position may not be that accurate, but this is the solution. Let me double check. So example 9.7. Example 9.7, and which is correct. It's 80 milliamp, which is correct. It's 0.08 ampere. Okay. Hopefully you can understand this low light analysis. And although the procedure looks complex, but the concept is simple. It's try to use a straight line to approximate the IV curve, segment by segment. And then from the configuration of the circuit diagram, you can configure the low line, and the intersection of each line is the solution. Okay, hopefully you can start working on your homework. And this is, we stop here.